I'm going to tell you about a quantum advantage for a natural streaming problem. So first, a word about what I mean by a streaming problem. Streaming algorithms are this class of algorithms for very large data sets that arrive one piece at a time. By very large, I mean much too large to fit into memory. And by one piece at a time, I mean that you start with an empty data set, and then it's presented to you as a series of small updates. For some examples, think of, say, you have a router, you're receiving this huge flood of network traffic information, and you want to calculate some statistics of it while only using the very small amount of memory that is available to your router. Or say that I give you the friendship graph of some very large social network as a series of events of the form Alice is friends with Bob, Bob is friends with Charlie, and so on. And you want to estimate some properties of this graph without having to store anything like the whole thing. Now, in the theoretical setting, the primary thing that we're interested in is the space complexity of these algorithms. So we want to know, for a given problem, what is the least amount of space that we can use and still solve it. This streaming model has a natural extension to the quantum setting. Rather than have your algorithm maintain a classical state, instead, you will allow it to maintain a quantum state. And then every time you see an update in the stream, you will apply some quantum channel to this state based on the update that you've just seen. Now, from the start of the study of these quantum streaming algorithms, it's been known that there are problems for which they require exponentially less space than classical algorithms. But this was initially shown for a problem that was constructed explicitly for the purpose of exhibiting this separation. Later, it was shown that for a very well-studied problem, the moment estimation problem, it is also possible to get a quantum advantage, but only if you have many passes over the input. So you see the entire input stream many times. So what I'm going to tell you about in this talk is a problem for which we can find a quantum advantage for streaming algorithms that only use one pass over the input, and for a problem that has been extensively studied in the classical setting. So what do we need if we want to find such a problem? Well, we need two things, really. We need a lower bound that proves that the problem is classically hard, and we need that lower bound of course, to not apply to quantum algorithms. And then we need a quantum algorithm that beats this classical lower bound. And as it turns out, there is a problem that already satisfies the first of these criteria. And that is the problem of counting triangles in graph streams. So this problem, in certain parts of the parameter space, has tight classical lower bounds that are derived from a reduction from the Boolean hidden matching problem. Now, I'm not going to talk about what the Boolean hidden matching problem is or how this reduction works here. But what you need to know is that this problem is, in fact, created to make exponential separations between quantum and classical one-way communication complexity. So therefore, any lower bound derived from it is not going to apply to classical streaming algorithms. And so this gives a nice potential candidate problem. And before I explain to you how we find a quantum algorithm that beats this lower bound for triangle counting, first let me just tell you what I mean by triangle counting. So this is a graph streaming problem. So we're going to receive this very large graph as a stream of edges in some arbitrary order. And what we want is to, at the end, be able to estimate how many triangles, so that is 3 cliques, there are in the entire graph. Now, it's known that even if you guarantee that the number of triangles is linear in the number of edges in the graph, you still need some additional parameterization to be able to achieve sublinear space. And so in this talk, I'm going to fix the following parameterization of the graph. We're going to have theta m edges, where m is a parameter that will be closely related to the number of edges, but for ease of discussion won't be exactly the same. And then there will be theta m triangles, and they will be edge disjoint. At the end of the talk, I will briefly mention how these results generalize to when these to other values of these parameters. So in looking for this improved quantum triangle counting algorithm, we're going to start by thinking about the case that was hard for classical algorithms, the what you get when you reduce from Boolean hidden matching. So this instance looks as follows. You start by getting an M star, and then you get a matching that possibly completes those on those outer edges of your M star, or outer vertices of your M star, that potentially complete the star to triangles. Now, how much space do you need to do this? Well, for some intuition, suppose that you just chose to keep k of the edges in this star. Then for each triangle in the final graph, you'd have a k over m chance of keeping each of its edges, so a k over m all squared chance in total. We've said that there are going to be theta m triangles, so you end up with theta k squared over m chance of success, and so you need to set k to be equal to root m for root m log m space. What the reduction from the Boolean hidden matching problem tells you is that this is pretty much tight up to a log factor. You need root m bits to count the number of triangles in this specific instance. So to start developing our quantum algorithm, let's start by trying to find an algorithm for this specific instance. In fact, let's make it even a bit simpler and just consider the case where we're just thinking of a two-player communication problem. So like Alice has a star, Bob has that matching, and Alice is going to want to send Bob some quantum message that he can then do something with to try and figure out how many triangles there are in the union of their two subgraphs. So the message Alice is going to send is going to be a uniform superposition over those outer vertices of her star. And she's going to send that superposition, which will cost her log m, O of log m qubits, to Bob. And then Bob is then going to measure that superposition. And he's going to measure it by constructing the following basis. For each edge VW in his matching, he will add V plus W over root 2 and V minus W over root 2 as basis elements. Because he has a matching, all of these elements will be orthogonal to each other. So he's going to be able to then take them and arbitrarily extend them to a basis of the entire state. And that's what he's going to measure Alice's superposition in. Why is this useful? Well, let's define the following random variable, x. So x is going to be 1 if his measurement returns one of these V plus W basis elements, minus 1 if it returns one of these V minus W basis elements, and 0 otherwise. And I claim that the expectation of x is 2t over m. Why is this? Well, for each edge VW in Bob's matching, recalling that U is the central vertex of Alice's star, if UVW is a triangle, then V and W are in the superposition. So v plus w will be returned with probability 2 over m, whereas v minus w will have dot product 0 with the superposition, so will never be returned. And in every other case, both v plus w and v minus w will be equally likely. If just one of v and w is in the superposition, then both of them will be returned with probability 1 over 2m. If neither v nor w is in the superposition, then both of them will be returned with probability 0. So that means that the expectation of x is just 2t over m. And since x has magnitude at most 1, clearly its variance is O of 1. And so by repeating this process m squared over t squared times and taking the average, you can get an estimate of 2t over m. Just log m bits is sufficient. Alice can send Bob m in just log m bits, so they can use this to determine t. And that this then gives a log m qubit protocol, because we've assumed that t is omega of m, as opposed to, remember, the root m bits that you needed in the classical setting. Okay, so for this specific communication version of one hard instance of the problem, we have this big quantum advantage. Now we want to get a quantum triangle counting algorithm out of it. So to do that, we're going to need to do two things. We're going to need to generalize Alice and Bob's inputs so that rather than having just this one, known classical hard case, they both have an arbitrary graph, and you want to know how many triangles there are in the union of their two graphs. And secondly, we're going to need to go from this two-player communication protocol to a fully streaming algorithm. So now let's start by generalizing Alice's input. Suppose Alice has a general graph, Bob still has a matching, and that matching may somehow complete Alice's graph to have some triangles. Now, where before we prepared a superposition over the neighborhood of that one big vertex Alice had, now we're going to construct a superposition over the neighborhoods of all of her vertices, which is equivalent to constructing a superposition over every edge that she has, except that every edge is now included twice in the superposition, once with each orientation. So when Bob goes to measure this superposition, for each of his edges VW, where before he was inserting V plus W and V minus W, now he's inserting UV plus UW, UV minus UW for every U among Alice's vertices. These basis elements are still going to be orthogonal, so this will still be a valid basis, and the expectation will behave as before, so we still have a working protocol. So now let's generalize Bob's input. What happens if Bob doesn't have a matching? Well, this is going to be a little more tricky, because if Bob even has two edges that share a single vertex, now he has UV and VW, and so two of the basis elements he should be inserting are U plus V over root 2 and V plus W over root 2. But those aren't orthogonal, and so they can't be part of the same orthonormal basis. So what are we going to do? Well, let's start by thinking about the case where Bob doesn't have a matching, but he does still have a low degree graph. Suppose that the maximum degree of his graph is D. Well, then what he can do is he can subsample his graph with probability proportional to 1 over D, and hopefully end up with a matching, and then measure in the resulting basis. Now we're going to lose a factor of D in the expectation of the estimator, because we've dropped each triangle with probability 1 minus 1 over D. And so we're going to need to repeat D squared as many times, which is all well and good when we're in this small degree case. But in general, Bob's maximum degree could be quite large. So this could still be a problem for us. But how much trouble can we actually get from this large degree case? Well, let's go back briefly to thinking about this classical hard case. So we'll go back to having Alice have a star, but we'll let Bob have higher degree vertices rather than just a matching. How many of the triangles in this case can be instant to Bob's high degree vertices? Well, in this case, all of the triangles are centered at that single central vertex, and they're all vertex disjoint. And so that means that each of them that touches a high degree vertex that Bob holds has to touch a different high degree vertex. And so because the number of high degree vertices Bob can have is limited by, you can have at most m over d degree d vertices, there can't be that many of the triangles that touch Bob's high degree vertices. And so if he just ignored those high degree vertices in constructing his basis, he wouldn't damage the estimate of the number of triangles that much. More generally, for there to be a lot of Alice's triangles that touch Bob's high degree vertices, they all need to be coming from wedges that are centered at different vertices that Alice holds, so that you can have a bunch of them that touch the same vertex. But it turns out that this is actually exactly the case when it's easy to count the number of triangles classically. So you have a situation where the hardest triangles to count with our quantum estimator are the easiest ones to count classically, and vice versa. So you can interpolate between the quantum and classical case, and that will end up giving you an m to the 2/5 space algorithm, as opposed to the root m that you would need with the best classical algorithm. And that m to the 2/5 then corresponds to kind of the triangles that are intermediate in difficulty for both the quantum and the classical estimator. So now we've generalized our two-player communication protocol. Let me give you a very high-level description of how you turn this into a fully streaming algorithm. What we're going to want to do, in essence, is treat every edge as both an Alice edge and a Bob edge. So every time we see an edge UV, we're going to want to add it to this Alice superposition. And we're going to do that by starting with a superposition over 2m dummy variables. And then when we see UV, we're going to swap two of these dummy variables for UV and VU in the superposition. Then we're going to take this, then we're going to do the Bob measurement. So if we call this edge VW, the part of Bob's measurement that corresponds to the edge VW will be measuring with three projectors. One onto the span of UV plus UW for all of the vertices U in the graph, then one onto the span of UV minus UW for all of the vertices U, and then one onto the remaining space. And by doing this, at the end, what we will get in effect is a result that matches for every triangle treating its first two edges as Alice edges and its third edge, as if it was an edge held by Bob. And that will give us a fully streaming algorithm that will get the same output as that two-player protocol. So now to wrap up, let me just put up the fully general version of the space complexity that you get when you generalize the parameters. And so when you compare this to the best possible classical algorithm, what you get with the parameter setting that I've been talking about in this talk is an m to the 2/5 versus root m separation. And that's kind of the setting of the parameters that maximizes the separation. Now, the best known lower bound that applies in the quantum case actually pretty much disappears when you have this parameter setting. And so it's still an open problem can you get a separation as large as exponential, maybe, for this problem?